in here, and I'll put a second router in. And I'm going to rename this one router 2. Makes it a little easier to understand. Okay, I'm going to just connect these two routers together with their Ethernet ports. Let me make them a little bigger on the screen so they're easy to see. And okay, I put these routers on the screen simply by, it was set on network devices. And the routers are on the list. If I wanted an Ethernet switch, I could click on this, and the lab that you're going to do for today, you're going to use an Ethernet switch and some PCN stations as well. I want to connect these two routers together with an Ethernet port, so I'm going to click on the red lightning, jagged lightning bolt thing, and click on the dark black line, which is regular Ethernet cables, and I'll just connect their 2 0 ports together, 2 0 0 ports together. So what we did before was we configured these routers with some different addresses, and we found that the routers could only connect to the directly attached networks, but they were not able to go over to the FAR router's Ethernet network and see a host machine or a loopback port. And in the last class, we talked about static routing. We would just create a default static route or a static route, and that would connect it to that. So just a little quick preview here of what we're going to talk about in the configuration. Let me drag this over here, drag this over here. I'm going to go into the first router, and I'm going to go to the command line basis, and let me expand it a little bit so it's we don't get so much wraparound. There we go. And I'm going to configure this with an address. Let's see, what kind of address should I use? Should I maybe use the address that's similar to what we're using in the lab? I'm going to use some simple addresses here. I'm going to make this router, let's see, interface gigabit 0/0, and I'll just make them an IP address, a very common address, about 192.168.1.1 with a regular old subnet mask. I'm also going to create a loopback port on this same router that, without any routing protocols or static routes, it should be unreachable from the other router. So I'll say interface loopback 1, and give them an IP address of, how about 192.168.2.1. That's a different network. You should be able to see that. Now, loopback ports are off automatically by default. So if we check with show IP interface brief, at this point, my loopback port is up and up, but I didn't tap the no shutdown command for the real gigabit Ethernet port, so I need to do that so it will be active. So I'll say interface gigabit 0/0 and perform the no shutdown command. And at that point, it should come up and up and up, up and up, up and up and up. Okay, I'll go to the second router, and let's do a similar function for the second router. So I'll go to the CLI. Is that showing on your screen? Good. Okay, good. It looks like it's an erase router. I'll say no to the prompt. And oh, I didn't give the other one a host name yet. Oh, bad practice from me. Okay, enable configure terminal host name R2. Let's not forget to do that when we come back to the first one. And I'm going to go to the interface gigabit port 0/0 on this one and give them an IP address of 192.168.1.2 because he's talking back to that other gigabit port. And oops, zeros and O's aren't the same thing, I guess. And then the no shutdown command. And then we'll go to configuration mode and interface loopback 1 on this one. And I'll give them an IP address of, how about 192.168.1.3.1. Oh, it's a sanity check. I'll do show IP interface brief. And we can see that these networks are up and up. My favorite little other command, which they're starting to finally talk about now in the CCNA curriculum, is show protocols. And that shows the same thing, except it shows you the slash number of the subnet mask. Show IP interface brief doesn't show you what the subnet mask is, but that's a quick way with show protocols to check for that. Now I'm going to go back to the first router, which is the one I forgot to give the host name on. So how about hostname R2? There, that makes more sense. So now if we look at the show IP interface brief, we see these ports are up, and in theory now I should be able to ping 192.168.1.2, which is the Ethernet port on R2, and it works. Or I'm sorry, I'm pinging my own address here. Let's try pinging the other one. There we go. So R2 is able to ping back to R1. Wait a minute, did I just name that R2 instead of R1? I'm going crazy here. Hold on a second. Show CDP neighbor. Yeah, I named it R2 by mistake. It should be R1. Okay, config T, host name R1. Okay. Now, and then we show CDP neighbor, and R2 is our neighbor through our gig 00 ports. And I was 192.168.1.1, and I was able to ping 192.168.1.2. And I was able to ping my own loopback port. I should be able to ping that. 192.168.2.1 is my own loopback port. But let's see, I shouldn't be able to ping the loopback port on the other router. Because if we go back and look at the other router, R2, show IP interface brief, he has that 3-to-1 interface. That's my own directly connected interface, so I should be able to ping it just fine. Do that. I can ping back to R1, 192.168.1.1. I can do that fine. But I shouldn't be able to ping that 192.168.2.1 address yet because I don't know how to get there. So it's going to fail. I'll wait for it to fail. So of course, routers only do what you tell them to, not what you meant them to. So when I show the IP routing table, I can see that router R2 only knows about his 2 directly connected interfaces, and he doesn't have any knowledge of that 192.168.2.1 that the other one has. So we put in static routes before. We would type a command like IP route 000.000, and then point to the exit interface, and that would take care of it. I'm not typing this in. I'm not even at the global configuration one, but that's an example of a command. Okay, but instead I'm going to use RIP. Just a quick preview of RIP here to see how RIP works. So if I type the command show IP protocol, right now there's no protocols running. There's no dynamic protocols running at all. So I'm going to go ahead and create the RIP protocol, just quick and dirty here to show how it works. So the command is router RIP. I call it letter RIP. And then I'm going to attach the networks that are my directly attached networks that were in my when I did show IP interface brief. I have 192.168.1.0, and I have the other network, which is 3.0. I don't put in 2.0. That's not my network. That belongs to somebody else's network. So now when I type show IP protocols, I see that I'm running the RIP protocol, and then I'm advertising these 2 networks out. Don't worry about these terms here. We're going to get more of this detail when we go through the slides. Okay, so I have information in one router, but I have to have the one in the other router for this, so they'll talk back and forth to each other. So I'll go back to R1, show IP protocols. Nothing's running. Let's quickly put in the RIP in there. Again, it's real easy to configure, just router RIP. And then what are my directly attached networks? I want to get mixed up here. Okay, 1 and 2. Okay, so I'll say network 192.168.1.0 and network 2.0. And give it a moment to converge. And then when we go look in our routing table, I see that I have that remote route generated from the other router. Sometimes it takes 30 seconds or a minute for this to take place before you can ping. But I ought to be able to ping that 192.168.3.1 address. That's that loopback port that's present on the other router. Can I dare try this 192.168.3.1? I can ping it just fine. So the RIP protocol has given this command for us, and we'll talk about some other advantages and disadvantages of static routing and other types of routing. And let me see, oh, I forgot to load the PowerPoint slideshow. Hang this 1 second, and I'm going to bring up the PowerPoint slideshow now, and we will perform death by PowerPoint. While that PowerPoint slideshow is loading, hang on just 1 second. I'm going to check attendance here. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, I think I got you all guys that are in attendance at this moment. Go back to share screens, share files. The Blackboard collaborator is converting my PowerPoint slideshow. And can I share it? No. Oh, share now. There it is. Okay. Okay, I hope you are seeing a PowerPoint slideshow that says Chapter 3 Dynamic Routing. And I should be able to click on this and go to the slides. Okay, so what we're going to do is this. Okay, is my mouse working? I hope my mouse is working here. We're going to look at dynamic routing protocols in general and a little bit of comparison of the old static routing and dynamic routing. And then we'll look at RIP version. RIP itself, RIP was originally just a RIP, and then it was RIP version 2, which fixed some earlier problems. RIP was one of the very earliest routing protocols that was ever developed. And then we'll look at how to read the routing table and a little bit about how the router makes this. You know, the router's job is to make the best path to termination to forward a packet to another network. And the internet routers that are at the ISPs that cost $1 million and are big, looks like a big rack mount server, they're the size of a refrigerator. They're very big. They might have 750,000 routes in their routing table. So they have a lot of lookup to do. Okay, so this chart shows some different types of routing protocols that have been developed over the years. RIP is a distance vector routing protocol, which means that it only has a hazy, neighborly view of the rest of the network. Link state routing protocols like the OSPF version 2 that we'll look at in a later course, they send, they're like I like to say that the distance vector routing protocol is like asking the guy in the gas station where to go to get to someplace, and he tells you, drive down 10 miles to the road to my buddy at the next gas station and ask him where to go next. Link state routing protocols are like having a roadmap, having a maps go, having a GPS, having a navigation system. All the routers have the exact entire topology of the whole company network in them, and there's no loops, there's no problems with stuff because everybody knows exactly where everything is. So RIP was originally developed in the early 80s when we first started using Ethernet, and everybody started getting connected together in this network that was a predecessor for the ARPANET, the internet that we have now. It was updated to version 2 to take care of some problems in the 90s, classless interdomain routing, variable length subnet masking, the ability to use different size subnets. So for example, in my first 8-week class, when you did that skills, paper and pencil subnetting exercise, they were all equal size subnets. They were all /28 networks with 4 host bits. In a RIP version 1 network, all of the subnets have to be the same size. That's not very scalable. I probably want a /24 for my offices. I would probably want a /30 for my point-to-point networks that go to the lease lines between the offices. So RIP version 2, one of the big things he fixed was the ability to have different size subnets. You weren't stuck with the same size networks. Other routing protocols that are link state routing protocols that have a more advanced features, Open Shortest Path First, or OSPF, is the one we'll see in the last 8-week course. At the CCNP level, there is one called Intermediate System to Intermediate System, the very unfortunately named ISIS. And EIGRP is Cisco's proprietary competition for OSPF based upon their original system, IGRP, which was their competition for RIP. These are interior gateway protocols that are used within a company. Border gateway protocol is used between internet service providers. And it also is a CCNP advanced routing topic. So we don't have to worry very much about that. So what do dynamic routing protocols do? Well, you know, when we did a static route, we just put the static route in and that told that router how to get to the other routers. But the problem with that is it has to be updated if you change the network. It's very highly secure. It doesn't waste any bandwidth between the routers. But most people use a dynamic routing protocol within their company network, like maybe RIP for a small company, maybe OSPF or EIGRP for a large company. And then they put in a single default static route to point back to the home office or to point back the path back to an internet service provider. So that means that if we add something to our company network, it's automatically updated, and 3 routers is not so tough. I want to go to 3 routers. There's a new engineering lab added, and I have to put in another line of code in all those 3 routers. Oh, that's not so bad. That's job security. What if I have 300 routers? That would be an overwhelming task. And what are the chances of putting in 300 configurations and not making a single error? So this way I can just add the new engineering lab to say off a new interface off of R3, and the RIP process will automatically advertise that, or whatever dynamic routing protocol will automatically advertise that to the rest of it. So dynamic routing protocols will discover new networks. They'll maintain up-to-date routing information even when something changes. They choose the best path based upon their metrics, which in the case of RIP is how many hops. More advanced routing protocols usually use bandwidth. And if one path becomes unavailable, they'll use an alternate path. So for example, R1's best path to R3 is straight through this one link. What if this link went down? Well, there's a backup path. I can go to R2 and then to R3. It's twice the cost, but I can do it. So this costs some CPU cycles on the router. He's got to run this program just like Microsoft Windows has to run another program when you crank it up. It has to take some CPU cycles and RAM memory and disk operations from that particular machine, and the routers and switches. It means it still uses CPU cycles. It still uses RAM. It still needs to load stuff back and forth from the flash drive instead of the hard disk drive. So the data structures, the tables, or databases that are kept in RAM memory, that incoming packets that are being lined up to be processed, the routing table structure. The routers also send messages back and forth to each other so they can discover their neighbors and share their routing information with them. In the case of RIP, he simply sends his entire routing table to his neighbors every 30 seconds. And then algorithm, thank you, Al Gore, for inventing the internet. Algorithm is just a fancy word for lines of code or a process or a flow chart that does something. So the RIP protocol has a certain process that he goes through when he determines how to choose the best path, how to update his neighbor. So most networks use both static and dynamic routing. We're going to use dynamic routing within our enterprise because I don't want to do static routing on hundreds of routers. I am going to create one static route that connects me back to my ISP, or maybe this is a branch office, and here at South Campus we use this connect back to the Trinity River campus. I'll use a default static route for that. So static routing is great, like in a stub network where you only have one way in and one way out. And this gives everybody in the company connectivity with each other using a dynamic routing protocol like RIP or OSPF, and still gives us a pathway to the 750,000 routes that are on the internet. We only have a few routes in our routers. We can use small $600 routers to do this. We don't have to have $1 million routers, refrigerator-sized routers at our small branch offices because there's just a few routes. Instead, we create one single additional default static route, and that points us back to the internet service provider. He's got the $1 million routers that can easily handle the 750,000 routes. So static routing is useful in these conditions. So static routing here is the advantages, very easily to implement in a small network. If you're not going to make any changes, you'll never have to update it. It's very secure. If you work for the National Security Agency or the CIA or something like that, you don't want to give away the farm. All your routing advertisements in a dynamic routing protocol give away a lot of information, kind of like Cisco Discovery Protocol gives it away. So in a static routing protocol, there's no traffic wasted. Doesn't use any CPU, doesn't use any RAM, doesn't use any bandwidth, and we have a predictable path to each destination. Okay, there's a downside. Only for simple topologies, or in the case of more complex companies, we're only going to use it for the default static route. If our company grows and we have dozens or hundreds of routers, it becomes very difficult to maintain the static routing tables. And if I need to reroute traffic, I would have to go and reroute them manually. Dynamic routing protocols are wonderful. If the traffic goes down, a link goes down on one way, he'll automatically reroute to the other way. It may take a minute, but he'll reroute, and eventually everybody will be able to continue their business operations. So how about a network like this? We got a couple of dozen routers. Wow. This is a good choice. Dynamic routing is a good choice for large networks. We're going to do dynamic routing, and if any new network is added in the engineering department down here, within a minute, everybody's going to know how to connect to that. If any links go down and a backup link has to be used, within a minute or so, we'll restore connectivity in case something happens with the company. And of course, one of these routers will be connected to the internet service provider. We'll establish a simple default static route and give that connectivity to everybody else in the company. More on that later. So dynamic routing protocols, if you got a lot of routers, dynamic routing protocols auto-magically do all this stuff for us. Small, large, medium-sized networks works in all size networks. Automatic rerouting of traffic. If there are multiple paths, duplicate paths, you can use them. Now, if you only have one path, then that goes down, you're stuck. But if you have multiple paths, and good practice is, try to have fault tolerance. If any one physical thing fails, we can continue business operations, so we don't have to pay our employees to drink coffee. Can be more complex to implement. RIP's fairly simple. OSPF's a little more complicated. It is less secure because the dynamic routing protocol is giving away everything he knows about. Now, it is possible to use passwords with some dynamic routing protocols to keep this more secure. The route depends on the current topology, and it does require additional CPU cycles, RAM memory, and bandwidth over the links connecting all the devices together. For example, RIP sends his entire routing table to his neighbors every 30 seconds. Every 30 seconds, all of your 300 routers are going to be flooding the network with all these routing table updates, even though it probably is not going to change for months or years. Okay, I showed you in the packet tracer, I went to the configuration mode and I said router RIP. If I decided I made a mistake in my router configuration, the wrong network number, I could just type no router RIP, and that would tear out that instance of RIP, and you could start again with a new router RIP and type in your new correct network numbers. Very simple configuration to go into the RIP procedure. Then I added a couple network statements. One of the routers was 1.1, one of the routers had .1 and .2, one of them had 1.3 and 2. I add those statements. These network statements, from the standpoint of R1, he has a 1.0 network and a 2.0 network. You only tell the router his directly connected networks, the .1 network and the .2 network. And he will advertise those to the other routers via the RIP process. 2 would only say the 2 network, the 3 network, and the 4 network. It would be a mistake to go to R1 and put in a directly attached network of .3 or .4. You're lying to the router. You'll get inconsistent results if you do that. So RIP version 1 is classful for IP version 4. Very old protocol, classful. Let's see, what's the expression? Rock and roll ended in 1975. Classful networking ended in 1995 when we had to implement variable length subnet masking and classless interdomain routing because the routing tables were getting too large with the ISPs. They aren't going to upgrade their hardware. They had millions of dollars worth of hardware that they hadn't depreciated yet. And in a business case, what you got to do then, if you can't upgrade the hardware, is rewrite the software. They rewrote the IOSs to allow variable length subnet masking and classless interdomain routing and network address translation and all the other tricks they did to keep the internet from falling over dead in 1996. And in a long-term environment, we're supposed to move to IP version 6. So RIP, the network statement, enables RIP on all interfaces that belong to that network. And then this will be advertised to all the other routers, which they do every 30 seconds. Okay, I showed the command show IP protocols, and it told me I was running the RIP protocol. It told me the networks that are being advertised. And when I typed show IP route, I saw my remember that directly connected networks in a router require no static or dynamic routing protocols. He can route between them automatically with no configuration required. You just have to make sure the wire's plugged in and you type no shutdown, and you configure the proper IP address. When a router shares information with another, in this case RIP-enabled router, I have my directly connected networks, and then I have some remote networks, some RIP-based networks that I've learned about from other routers, and now I know how to get there. They're in the routing table. So these days, I probably want to use variable length subnet masking or classless inter-domain routing or other newer features if I'm still using IP version 4 and I have not yet moved to IP version 6. So the version 2 command takes care of some defects that were original in the original, RIP version 1, the original version of RIP. The original version of RIP broadcasted his routing table to its neighbor every 30 seconds, and broadcasting is very intrusive. RIP version 2 multicasted, which is a kinder and gentler way of sending a message in all caps, is what I call a broadcast. It's very intrusive. The second thing that RIP version 2 did is he allowed variable length subnet masking and classless inter-domain routing. The original version of RIP only set the network prefix, but no subnet mask. That's why we had to use the same subnet mask everywhere. RIP version 2 sends the network prefix and the subnet mask to all its neighboring routers. And now we're free to use different subnet masks in our topology. So I could make an office, a /24 with 250 odd hosts. I could make a point-to-point network between two routers, between branch offices, a /30, which only consumes 2 network addresses. That would be better. So we can use the command show IP protocols and see whether it's version 1 or version 2. This router has been promoted to version 2, and now it says it's running, sending and receiving version 2 updates. There is a compatibility feature in Cisco devices that if you're upgrading your dozen routers in your company one by one, version 2 routers will have some limited connectivity backward compatible with the version 1 routers you have not yet updated. So you won't completely ruin your communications within the company when you do that. Or you could just do it over the weekend. Auto summarization is a feature that's built into the original RIP that cannot be disabled and can cause a problem when people split their networks and use their IP addressing in unwise ways. It can lead to a situation in which pings can work half the time. In RIP version 2, auto summarization is on by default, but you can use the no auto summary command. So if you start working for a company, always blame everything on your predecessor who had bad design. And if he has a problem here, that summarization is on, you can turn it off, promote it to RIP version 2, turn off auto summarization, and that might fix your problem where half the pings fail. So when I do show IP protocols, it tells me that automatic summarization is not in effect. Someone type no auto summary. Otherwise, it would say by default, automatic network summarization is in effect. Passive interfaces is a feature that between the routers, we have to have the RIP updates go between the routers. Otherwise, they won't be updated. But what about these 3 gigabit ports that go to no further routers and just go to employee workstations? They don't need to send and receive RIP updates. They don't need to hear the routing table every 30 seconds. If it's old RIP version 1, it's going to be broadcast. It's going to slow everybody's PC down. So the passive interface command allows us to specify, for example, in this environment, let's specify this Ethernet port on this router R1 to be in the passive state and don't send and receive updates at that interface. So these guys attached to this switch will never hear the broadcasts. Well, you're probably saying, well, I won't put in the network statement for 1.0. That would do the same thing, but unfortunately, they would have no connectivity because the RIP router hasn't been told to advertise their presence to the rest of the network. So we can go to the router RIP prompt config-router and say passive interface gigabit 00, and no updates will be transmitted at this port anymore. And these guys, all these workstations, 200 workstations, employee desktop PCs won't have any kind of won't hear any kind of broadcast or a multicast if it's RIP version 2. Every routing protocol has this feature. This is how we implement it in RIP. So when we do show IP protocols, it tells us we have passivated, we have keyest, we have quieted down that gigabit Ethernet port. He's still connected, but those devices there don't go to any router, so we don't need to send the updates there. Now, dynamic routing protocols send information about all the directly connected networks to all the other routers. So I need connectivity for the internet, for my people to talk to business partners and customers on the internet. But I don't want to import the 750,000 routes of the internet into my small branch office routers because they don't have the horsepower to handle that. It would be like trying to use a cheap prize desktop machine and being the Active Directory domain controller for the entire college with 100,000 students. It wouldn't be able to do it. It would crash. So instead, what we do is we run a dynamic routing protocol like RIP within our company with our few routers. Our little bitty branch office routers, they're less than $1,000. They can handle that just fine. And then we're going to create one default static route to our internet service provider. This red jagged lightning bolt is a serial connection. It could be Metropolitan Ethernet or Carrier Ethernet also to our internet connection. And what we want to do is create a default static route on R1 because he's the one that's directly attached to the internet. So he puts in the command IP route quad 0 S00/1 is the serial port off that router, and he's added the next hop IP address, which is the IP address of the internet service provider's router that's back at the ISP. And then when you go into the router RIP command prompt and it changes the config router, I don't want to have to go to R2 and R3 and create a default static route for all of those. Well, 3 is not a problem. What if it were 300 routers? So instead of duplicating the command over and over again on all the other routers, I'm going to add one more line of code in R1, default information originate. And that's going to propagate that default static route that I created on R1 on all the other routers using the RIP process, which is sharing anyway. He's sharing all the network information anyway. He can do that easily. On the original router R1, a default static route shows up as S*. That's the gateway of last resort has been set. On all the other routers, it'll show up as R*. It was told to R2 and R3 from R1 over the RIP advertisements. Okay, let's look at the routing table entries now. So here is a network with some routers, and they have created a static route to the internet, and they've a default static route to the internet, and he's tapped the show IP route command. And here we see our routing table. We have some directly connected networks. In the case of R1, he's got the direct connection to the ISP server. He's got the direct connection to some employees connected to an Ethernet switch. And he's got a serial connection that goes to a second branch office for that company. That second branch office has got some employees that have their own Ethernet switch at that physical location. Then that second branch office, R2, has got a serial connection to the third branch office that's connected to his company, and he's got a serial port connection to some other location. So we see these directly connected networks. From the standpoint of R1, he only sees 3 directly connected networks. All the other networks have the R prefix in the routing table. He learned that network. The .3 network is not physically connected to R1. It's one hop away on another router, but he knows how to get there. The RIP process educated him on how to get there, and he says, "Oh yeah, if I receive any packets for 172.192.16.3, just send it out my 000 port, and it'll get there." The router did his part. He sent it one hop over. Router R2 will then send it to this directly connected guy. If it was for another guy at another office, he would send it on to the third router. And hop by hop, it would get there. Directly connected networks have the C prefix, and in the newer iOSs, they also have the L prefix. The C prefix is the network entry, like a /24, a 255.255.255.0 base network with 250 odd hosts. They're directly connected. And then he has I call it a link local entry. That's the exact IP address. A /32 is a host address. Hang loose 1 second here. I have to check attendance, and I'll be right back here. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, good. We're good. So when you look in the routing table with a show IP route, you'll see some C's and L's corresponding to each one of your directly connected interfaces on that router. So if you turned on 3 of them, you'll see 6 lines. You'll see 3 C's, you'll see 3 L's. And they'll identify that interface port. In this case, it's the first Ethernet port. How did he learn? Well, it was directly connected on that router. What is this network? He gives us a network portion. So any packets received by this router that are 172.16.1.anything will be sent out the gigabit 00 port. Other prefixes possibilities include S if it's a static route. It includes D if it's an EIGRP based update, O if it's an OSPF, or R for RIP. At the CCENT level, we're just concerned about the RIP and the static. So when we look at an entry, in this case, the prefix is R. And by the way, every time you type show IP route, you get that legend at the top that shows you all the different abbreviations, what they stand for. I've lost my mouse. There it is. Okay. Then we have the destination network. Any packets that flow into this router that have a destination address of 172.16.4. Some numbers is a /28 will be sent out the 000 port, the exit interface to the outgoing. The administrative distance is a measurement of it's like the Boy Scout oath: trustworthy, loyal, helpful, friendly. It's a measure of the sophistication of the routing protocol. The lower the number, the better. So RIP is 120. If we were also running OSPF on this router, which is a lower administrative distance, 110, the OSPF information would go into the routing table and the RIP would not appear. The metric is how we determine the best path. If there's more than one way to get to that destination network, which path do I take? And metrics are like the 50-yard dash, the lower number is the better. Okay, the guy that runs the 50-yard dash at 7.5 seconds is a better guy to start than the guy that ran it in 7.8 seconds. So if it's 2 hops to the neighboring network and there's another way and that's 5 hops, that's more latency. I'll use the 2-hop method. RIP only measures hop count. He has no concept of bandwidth or link speed. The more advanced routing protocols like OSPF and EIGRP generally measure speed, and they'll choose a path that has more hops but has faster links over a path that has an accumulated link that's speed that's slower. The next hop is the IP address on the other side, not this router's IP address, but who to send it to, so it can get to the next hop router and be handled. And RIP sends this advertisements out every 30 seconds. In this case, I last heard from this router 12 seconds ago. If it climbs to 30 seconds and I fail to hear an update, I'm going to wait. I'll say, well, maybe I just missed it. I'll wait until another 30 seconds elapses. And after a sufficient interval passes, between 3 and 4 minutes, the router will decide that he's lost the connection to that network and he'll take that route out of the routing table. Okay, this is Cisco mumbo jumbo here, but let's think about ISP router that has 750,000 routes in it. Every single individual packet that flows into that router, he's got to go to the routing table lookup process and look through 750,000 lines to determine which line I should use, which exit interface or next hop IP address should I use. So the Cisco engineers have put in some advanced lookup features. You programmers, you might call this binary tree lookup, B-tree, that allows the lookup process to proceed more rapidly. And what it does is kind of like indentation in an executive report for a C-suite type of guy. You want to reduce everything to 1 paragraph to him, and you get 4 or 5 indented reasons why we should be allowed to buy this new server, this new router. This sort of places a method in the routing table where they can very quickly skip through without having to look through all 750,000 lines and very quickly indent themselves down to an entry that matches where they need to do to be able to deliver. So ultimate route. An ultimate route is a routing table entry that contains a next hop IP address or an exit interface. So these entries in orange, they have an exit interface or a next hop IP address. A couple of entries here don't contain exit interfaces information. So all of these 172 dot addresses were subnetted from this original 172.16 Class B address. So if a 172.16.anything router packet flows into this router would first go to this line and say, well, the first two dotted decimal values match this. Jump to this section of code now for your precise lookup of exactly where to go to. Don't pay any further attention to the other 749,000 lines. This greatly speeds the lookup process. So ultimate routes are routes that actually, they're probably a subnetted network, and they actually have the Ethernet port or the serial port that tells you how to get there. Directly connected routes are always ultimate routes. Local routes, dynamically learned routes are always ultimate routes. Okay, now we'll go to child and parent routes. Level 1 routes, parent routes. A level 1 route can be a network route, which has a subnet mask equal to that of the default subnet mask. It could be a supernetted route, for example, summarization, or it could be a default route, which is the ultimate summarization of all possible addresses. Now, routers will look for the line that has the most bits in the network prefix that matches. So if I got a /24 and a /28, and they both have the same prefix, I'll use the /28 because it has more bits that match. It's a better match. So if I have a default route that takes me back to my internet service provider, and someone types an address that's on the internet, it won't be any of my interior company IP addresses. So he will look through the major he'll look through the major level 1 route for the 172.6 and the 192.168. He won't find any matching entries in that. And a router will normally drop a packet if there's no matching entry, but we'll say it doesn't match any of our interior corporate routes. It must be some route out there on the wild west of the internet. Send it to that serial port that goes to my internet service provider, and it'll be sent there. So level 1 parent routes is a level 1 network that's been subnetted. So here we have 172.16/16, default subnet mask for Class B. And here are the subnets that have been created for that network, .1, .2, .3, .4. So level 1 parent routes, he looks up and finds that first. Then he says, oh, I don't have to look through the other million lines of code. I'll just look at these 5 lines for this network at this company, and I can more rapidly look up because I need to determine, do I go out the Ethernet port? Do I go out the serial port? Depends on what subnet it is. Much faster lookup process by using this technique that the Cisco engineers came up with. A level 2 child route is a route that is a subnet of a classful network address. So we have our parent route, and then we have our children routes. Parent route level 1, child routes level 2. Level 2 routes are ultimate routes because they have an exit interface like Ethernet or serial port. So nothing confusing about this. The router receives a packet, and if it's a level 1 ultimate route, that route is used. If it's a parent route, that means it's been subnetted. Go look in the children routes and look for the one that's the best match. If there's no parent route or child route that match, look for a default route or look for a summarization route. If no match is found, a packet is dropped. Of course, if you've established a default static route, everything that doesn't match the internal company network addresses will be sent to the ISP, and he'll be able to match it to a real network address that's on the internet. Okay, longest match counts. So I've got several entries in my routing table. This one only 12 bits match. This one 18 bits match. This one 26 bits matches. The longest match trumps and becomes the winner of which route is chosen because it has the best match. So routers always go for the more bits that match would be a better entry. IP version 6 is treated slightly differently because there's in IP version 6, they're all considered level 1 ultimate routes. So in this case, we've got these 1, 2, 3 point-to-point networks and 1, 2, 3 Ethernet-based networks. They're all considered ultimate routes when they appear in the routing table. And another weird quirk of IP version 6, if you've established a default static route, it doesn't say S* as another nomenclature. So when we look at a show IPv6 route, we would show IP route for IPv4, show IPv6 route shows our IPv6 entries, and we have a directly connected network. We have a link local address. The rest of the routing table is similar. The administrative distance, it's directly connected, so nothing is better than 0. That's the lowest possible value. The metric, the metric is 0 since it's directly connected to this device. There's no hops. And then we have the exit interface to use 000 to get to that. Very similar otherwise to IP version 4. So here's not a directly connected network on this IPv6 router. The D prefix tells us it came from EIGRP. They couldn't use the letter E because it would have been taken away by an older protocol called Exterior Gateway Protocol, EGP. No one uses that anymore. They use Border Gateway Protocol, BGP, but the letter E has been taken. So in the case of EIGRP, they use the letter D because EIGRP uses a path determination thing called the dual algorithm, so they named it D for dual. Next hop address and the destination network is listed. The metric, the administrative distance of EIGRP is 90. So if it was a fight between EIGRP and RIP, EIGRP win because it's lower. No, we normally don't run multiple protocols on one router. But if you bought a company and you were running OSPF and they're running EIGRP, you might have a short period of time where the gateway router between the two companies would have to run both routing protocols. Here's the metric for EIGRP. It's not a hop count. It's based upon bandwidth. So it's a complex number. It's usually a 7-digit number. But lower wins if there's more than one way to get there. Okay, I'm going to skip now to getting started in this lab that you guys have an assignment for today and show you some of the gotchas with it. First of all, let me share the first page of the lab. No, I don't want to share files, sorry. I want to share, I'm going to share the screen. I'm going to share, oh, I got to bring it up. It's not appearing on the screen here. Hang loose 1 second. Here we go. Okay, here's the first page for the lab for this chapter for RIP routing protocol. In this lab, you're going to set up a 3-router configuration, 3 host machines, 2 switches, and this one's direct. Here's the first gotcha in this lab. These routers use G01 and G01, and then they hope you're not watching. The top router uses G00. So be careful when you set these up and you configure the proper interfaces. Then there's a chart that shows the interface assignments for all of these. But here's the biggest gotcha, the serial ports. The 1941 router doesn't have any serial ports installed in it by default, and we have to install this serial port in it. So let me step through how you would do that. I'm going to share Packet Tracer again to show how that's done. Okay, I'm going to put this away, and I'm going to start building this topology that we're going to use in today's lab. Okay, so we have 3 routers. I'm going to pull the 3 routers in here. The 19, I'm going to click on the network devices, click on the router, choose a 1941, and let's pull some of these routers in here, and then I'll make them a little bigger where you can see them. I can make that bigger like this, a little bit bigger. Okay, so when I'm going to look at this router, and it tells me that it only has 2 Ethernet ports. Well, let's look at it. So here we go. Here's a picture of this router. Now our routers have got a serial port here, and they've got that little 4-port Ethernet, 4-port switch like a home router's got over here. So I want to put that 2-port router, 2-port switch. There we go. I'm sorry, my pointer was, there we go. So if I click on this and try to drag it over there, he says, oh, just like in the real world, you can't plug in an option card to a device when it's still powered on. So see this little teeny weeny power switch? I'll turn it off. Then I'll drag the switch up. I'll drag the 2 serial ports up there. Okay, now it's been provisioned. Now I'll turn it back on. And if you look at the CLI, you can see it's starting to boot up. Okay, I need to repeat that process for the other 2 routers and install a serial port in them. So I'm going to turn off the switch, click on add the serial ports, turn the power back on. Did I turn it back on? Is it on? Check, should be booting. Okay, it's turning back on. And then I'll go to the first router, turn off the power, add the card, restore power. There we go. If I hadn't done that when I went down to the jagged lightning bolt thing and tried to choose the point-to-point links, it wouldn't work because they're available. Now if we look at these routers, yeah, they have serial ports. All 3 of them got their serial ports. Yeah, same exact port numbering scheme that we use on our road routers in the lab. Unfortunately, we've all, even me, even all the TCC employees and teachers, not just you students, we've been kicked out of campus. We can't go back until later. Okay, so I'm going to plug these together. And the lab topology calls for serial port 000 of the first router going to port 000 of the second router. This is a standard serial lab topology that we've used in Cisco for over 10 years now. Now I'll go to the second router, and that port 0001 goes to port 001 of the third router. Now they're connected together, and we can proceed with the configuration of the routers. I'm going to, let me see, I'm going to make space on the screen here where we can show the other devices because there's some switches and there's some host machines in here. And we'll make sure it shows up on your teeny weeny screen that you guys get. Okay, now we're supposed to attach some switches to R1 and R3, and the host machine on R2, the host machine, the PCB gets connected to it directly without a switch. And you can do that. You can plug a PC straight into a router, and because of the auto MDIX feature, you don't have to have a switch in between it. You just limit it to one computer attached to that router. You normally would plug a router to a switch and then plug 24 devices to the switch and give all those 24 employees the connectivity to the router for that department of the company. So I'm going to go back to the switch and choose a 2960 switch, and it's supposed to go to router 1 and to router 3, and let's see if I'm going to be allowed to change its names. Oops. There we go. I want to make this switch 3, make this switch 1. There's no configuration of the switch required in this lab. If you look at the addressing table, it says for switch 1 and switch 3, no VLAN assignments required, no port security, nothing like that required. If you did this in a real physical lab, like in our laboratory room, you'd have to check and make sure that no previous student had left in pre-existing configuration on that switch. So you need to check and see, for example, that it has no startup configuration. It's asking you the question, it has no startup configuration. You also have to go on a switch and check to delete the VLAN.dat database file. But in the Cisco Packet Tracer program, when you provision a switch, it's completely erased. There's nothing in it. Well, we'll just prove it. I'll pull up a switch. I'll go to the CLI. And I'll go to the privilege exec mode, no passwords required. Show me the startup configuration. There's none. Is there any VLAN file present? No. This switch is completely ready to go. Good. We won't need to mess with this switch anymore. I'm going to have to really scrunch these guys together to get to fit in the screen. Oh dear. I'll drag this up there and drag this up here and drag this up here and drag this up here because we need to put some host machines in here as well. Okay, let's connect according to the lab topology. Let's connect the switches to the PCs, rather to the routers, and then I'll put the PCs in there. So I click on the red lightning bolt thing, and I'm going to choose solid Ethernet cables. And switch 1 is supposed to be connected via port number 5. It's off the top of your screen, but really it's port number 5. And it goes to the router's port number G01. And on the second one, on switch 3, it's supposed to be, again, port number 5. It's off the top of your screen. And it goes to port G01. The tricky one is the router up at the top, which uses no switch. So I'm going to go and click on the devices and go to this little icon that looks like servers and workstations. I'm going to choose a regular PC, and I'll put that PC. I'm going to have to put it up kind of over here to the side here because there's not much room for it. And that's going to be our PC-B. And I'm going to connect them with a solid Ethernet cable, a straight through Ethernet cable. Ethernet port on the PC, and it's supposed to connect to port G00, not G01. I hope you're not watching there and that you'll make a mistake. Now let's connect PC-A to switch 1 and connect PC-C to switch C. So I'll go through and I'll choose, again, I need to choose the host devices and a PC, and I'll put one here, and I'll put one here, and it's coming off the bottom of the screen. And let me correct the nomenclature. This is PC-A. And this PC/C. And this is appear on the screen. Good. Okay, good. We can see this. Good. One second. Hang loose 1 second, guys. Okay, let's connect our PCs. I'm going to click on the lightning bolt connection, click the regular Ethernet cable, and PC has one Ethernet connection. Most PCs just have one. And that's lab says a CAS test port number 18, which you can see on this one. And PC-A is supposed to attach to port 6 usually. Usually PC, the first one goes to port 6. Notice something weird here. The green light has come on the switch port going to the PC because by default, PCs are active, and switches by default out of the box, as soon as you plug a wire in, it stays amber, orange for about 30 seconds, and then it turns green. So it's turned green. Our router ports are still shut down. So as soon as I go and do a no shutdown on these 3 routers, this port, and after about 30 seconds, all these lights will turn green, and we'll be able to connect to it. Same reason this PC is connected to a gigabit port that's shut down right now. It's down. It's down. Can't connect to it. So what I like to do whenever I do a lab is just to make sure, as a sanity check before I waste a bunch of time, and I'm not plugged into things that are proper. What I would like to do is simply give all the devices their host names and shut down all interfaces, like on routers that are shut down by default administratively, and then use Cisco Discovery Protocol to make sure that sanity prevails here and we're actually connected to the devices we wanted to be connected to. I see a lot of times in the real physical lab at school where people will flip a console cable and they think they're connected to one router and they're not connected to another one, and they don't get the results that they hope to get. So I'm going to start with this first switch, and I'll go LI, and I'm going to give it, go to the privilege exec mode, go configure terminal, and give them a host name of, that's supposed to be S1. That's all I need to do on that switch. I'll go to switch 3, go to the privilege, I'm already at the privilege exec mode because I checked this earlier. Go to the configuration mode and give them a host name of switch 3. The PCs are, we don't have to rename those. Those are just host machines. And the PCs, we'll look at them in a minute. They are a sort of a stripped down, kind of like a Windows workstation. some of the IP configuration stuff's not exactly the same as what you see, and some of it's similar. We'll show you that in a minute. Let's do our routers. Go to router R1. Go to the command line. Looks like it's an erase router. It's saying no. It's saying, do you want to go in the configuration dialog? Go to privilege exec mode. Show me the startup configuration. There's nothing in here. It's an erase router. We just provisioned it. Okay, so I'll go to the global configuration mode and give him a host name of R1. I'm going to go ahead and shut down all his interfaces. I mean, turn on all his interfaces that we need for this lab. So show IP interface brief. Oh dear, let me make this bigger so we don't get the wrap. There we go. Okay, so I've got 2 gigabit ports and 2 serial ports that have nothing assigned to them, no IP address, and they've been administratively shut down. In this particular R1, he needs the G01 to have an address, and he needs his S00 to have an address. So I'm going to go ahead and go back to the configuration mode and say interface gigabit 0/1. Do no shutdown. Give him an IP address. You can do it in either order, doesn't matter. And R1's gigabit put is 172.30.10.1. And it's a 255.255.255.0. He's going to use some /30s on the serial port. So I'll go to interface 0000. You can go straight from the config-if to another interface port. You don't have to back out and go back to the enable mode and go back to the configuration mode. You can do it straight from here, and you can abbreviate just like you normally would. So now at config-if, I'm on the serial port now. So IP address. That serial port is specified as 10.1.1.1 with the 255.255.255.252, which is a very small network, perfect for point-to-point networks because it only has 2 usable IP addresses. I'll perform no shutdown on that. Now, serial ports are kind of funny. This serial port's not going to really be able to come up and up. Oops. This serial port's not going to be able to come up until I go to the serial port on router R2 and make him come up on a serial port. Both sides have to be talking the same language for them to come up and up. Okay, I'll go to R2 now, and let's see if we can get him going. Go to the CLI, bring it over here where it's visible to you guys. Okay, answer the configuration, no. Privilege, go to the privilege exec mode, go to the configuration mode, give them a host name of R2, and let's, all his ports are shut down. Don't have any IP addresses assigned to them. Let's go ahead and assign those IP addresses. In the case of R2, there's 1 gig port and 2 serial ports. The gig port goes to PCB. The 2 serial ports on the left talk back to R1, on the right talks forward to R3. So let's take care of this. I'll do interface gigabit 0/0, not 1. I want to see if you're paying attention here. And IP address is given for PC. For R2, gigabit port is 209.165.201.1, which looks like a valid, globally unique kind of internet address. It's actually a reserved address for training and documentation. And that address is 255.255.255.0. And then perform the no shutdown. Now let's take care of our 2 serial ports. Interface S0/0/0. IP address for S000 is 10.1.1.2. That talks back to the 10.1.1.1 on router R1. 255.255.255.252. Shutdown. Interface S0/0/1, the one to the right. IP address of that one is 10.2.2.2. It's working right here. IP address 10.2.2.2, 255.255.255.252. No shutdown. And if we look at that show IP interface brief on that guy, we can see that, look, the gigabit port, of course, came up and up. It's got a host attached to it. The serial 00 went back to R1. We've already configured R1. It's up and up. But look at serial 001. Let's see. Can I see it can't come up yet. It's not administratively shut down. I did not shut down. As soon as we configure R3, it'll come up and up. Okay, so let's take care of R3. All this just to show Cisco Discovery Protocol. But you have to do all this stuff anyway, so that's why I suggest doing it. Okay, enable mode, configure mode, host name, R3. R3 has got a 0/1 port, and his IP address is going to be R3 is 172.30.30.1. No shutdown? Did I do that? Okay, interface S001. IP address at that, which talks back to R2, is 10.2.2.1 and R/30. Shut down. Show IP interface brief. Hey, everything's up and up. Show protocol, which is my favorite shortcut, shows the same thing, but it shows you the addresses and the slash number or the subnet mask. Show IP interface brief only shows you the network that does the IP address. It doesn't show you what the currently assigned subnet mask is. So they're starting to put show protocols in the labs now. I'm glad to see that. It's a good alternative to show IP interface brief. Now, if we do show IP route, we have our directly connected to networks. I haven't started a RIP yet. There's no connectivity. So if I try to ping, I should be able to ping across my point-to-point link to router R2's 0001 port. That's 10.2.2.2. Yeah, I can ping him. No way am I going to be able to ping that gigabit 00 port. No way in the world can I ping that gigabit 00 port 209.165 or 201.1. No, it can't work. There's no 209 information in the routing table. It can't be delivered. The ping will fail. Finish failing. I have to wait for them to fail. There we go. So similarly, when we look at the other routers, they're only going to be able to ping their directly connected interfaces with the devices on their interfaces. I have forgotten to put in the IP addresses of the host machines. I must show you that. So let's go to PCA first of all, and I'll show you the weird interface that he's got for this. Okay, we're on PCA, and I'm going to go to the desktop, and I need to do the IP configuration. Oh, let's see now. We're going to do static configuration, and PCA is supposed to be 172.30.10.3. Oh, look, he fills in the subnet mask, kind of like the real machine would do. And his default gateway, his friendly neighborhood router for PCA is 172.30.10.1. That should stick if I do that. Go back to the desktop. Oh, let's see. I'll do it this way. I'll click on it one more time. Go to the desktop, and I want to go to the command prompt. Did this stick? Did this configuration stick? Oh dear, did it not stick? Hold on, let me try another method here. I'm going to go to the. Oh, I was doing PCA. I was doing PCA. Sorry. Did I do the wrong one again? Command prompt. Okay, so it kind of looks like Windows. 172.30.10.3. I should be able to ping my default gateway. Should I be able to ping 172.30.10.1? It's my own default gateway. Hey, it works. Pretty good copy of Windows, isn't it? I won't be able to ping anybody else because we haven't put any RIP connectivity in yet. Okay, PCA is configured. Let's configure PCB. Go to configuration, IP configuration, and PCB he is told to be 209.165.201.2. Oops. 209. I typed the wrong character. 65.201.2. The default gateway is 209.165.201.1. That should take care of that guy, and let's see if he's able to. I guess I have to open it and close it again to get this. Go to desktop, go to the command prompt, type ipconfig, and did I make any typos? I should be able to ping 209.165.201.1. I can ping my own default gateway. Okay, good. Okay, let's take our CC, and then I'm going to illustrate the show CDP neighbor thing to prove that all our routers are connected properly. I'll go to TCC, click on configuration, or rather click on desktop and IP configuration. It's all in one screen. There's another way to do it from separate screen. This is a little easier. PCC is going to be 172.30.30.3, regular old subnet mask. And his default gateway is 172.30.30.1. Go to the command prompt, ipconfig, and I should be able to ping my own default gateway. Okay, that works pretty good. Okay, now let me illustrate. I'm going to start with the man in the middle, R2. Go to CLI. And I'm going to ask router R2 to tell me who are his directly neighbors using something called Cisco Discovery Protocol. And I can see that, let me see, the mouse when I'm moving down here doesn't appear on. Let me put the mouse up here and see. Oh, there's a bug in this packet tracer software. We can't see the mouse on it. So what I'm going to do is draw your attention to the bottom of the screen where it says the R2 # prompt. Directly above that line is R3 and R1. Okay, R3 0001 port connects back to the 0001 port of R2. R2 000 port goes back to the 000 port of R1. So we've confirmed that we can see the line that says local interface. It says device ID local interface about 4 lines up from the bottom. Local interface is the serial port on the ports on this router R2. The one that says port ID at the end of the line, that's the remote identification of the serial port on the remote router. So it's supposed to be R1 to R2 through 000 to 000. It was supposed to be R2 to R3 from 1 to 1, and it is. So we've confirmed that they're connected properly. Now, it only shows your directly connected neighbor. It won't show, for example, we just looked at this from R2. This is directly connected. I saw R1. This is directly connected. I saw R3. I didn't see the PC because PCs don't run Cisco Discovery Protocol. It's proprietary to Cisco. There's another protocol we'll look at later called Link Layer Discovery Protocol that can run on PCs. That's what, when you go into the network neighborhood of your PC, it shows you how you're connected to the internet. Let's do it on R3 and see what it sees. That's why I had to give host names to the switches, because I wanted to make sure that this worked. Show CDP neighbor. And I can see that I'm connected, of course, to R3 connects back to R2. You can't see R1, it's a couple hops away. R3 is also connected to the switch S3. And we can see the port numbers. Yes, the gigabit port 01 was supposed to go to the fast Ethernet port 05. So that's all working properly. Now, I'm not doing this whole lab for you. I'm showing you some setup stuff, but I'm going to put some basic RIP configuration in here just to show that activity could take place. PCA ought to be able to ping PCB. PCA ought to be able to ping PCC. Everybody should be able to ping anybody else in the topology. So let's go to these 3 routers and add some RIP information and see if we get connectivity here. He's going to have you do more stuff in the lab, like the passive interfaces and the disabling the automatic summarization and things of that nature to show you some of the more advanced features of RIP. Well, I'll go to router 1 first. He timed me out. So go to the privilege exec mode, go to the global configuration mode, let her rip with router rip. And what are my directly connected networks? R1. Well, I've got 172.30.0.0. Because that's the classful. It's classful. We didn't make it version 2. I'm going to try this just for fun. I'm going to specify the /24 address. I'm also going to say version 2 to promote this router to version 2. We're not using a bunch of weird different subnet mask here. It should work without it, but I'm just for safety, I'm going to turn it on. It's a little bit more advanced. My other network on router R1, the 10.0.0.0 network. So if I do show IP protocols, yeah, I'm advertising the 10 network, I'm advertising the 172 network. Both interfaces on these have one of those as their original parent or major network. But I won't get connectivity until I go to R2 and R3 and finish this process on them as well. So I'll go to R2 next. Go to the global configuration mode of R2 and specify the 3 directly connected networks. However, I'm going to get away with fewer network statements than this because I have to do router RIP version 2 and network 209.165.201. By the way, if you type the whole host address, this is one thing that really bugged me when I first started learning RIP. I thought the router was broken. I've typed the entire host address here. I haven't typed the network it came from. But watch what happens. Now when I do a show IP protocols, it reduced it. The mouse work up there? No, not in these entries, it doesn't. It reduced my host entry to the 209.165.201.0, the network it came from. It reduced it to the classful network it belonged to. That bugged me for a long time. I said, what happened to my one? And I would reload her and start all over again. And finally I figured out, oh, it's the network, not the host address. So you can type in the host address, and if you don't know how to subnet and find the network identity for a particular host address, the router does. He'll gussy it up for you, as we say in East Texas. He'll fix it up. So it's working okay. Okay, I've added one network, 209.165. I got to go back to the configuration mode and go back into router RIP and add the other network, which was 10. We have 2 networks, but they're both part of the major network 10. That should take care of that. Now let's go to R3, do something and see if we can get some connectivity here. Configuration mode for R3, router RIP, and the networks on R3, there's a gigabit-based network and there's a point-to-point based network. So on R3, I'm going to say network 172.30.0.0. If I type the 30.30 or the 30.30.1, he reduced it to 30.00 because it's classful. And the other network is isn't it the 10 network? Yeah. In a real network, it can take up to a half a minute or a minute for conversions to occur. Conversions is defined as the moment in time after which all of the network routing tables are consistent with each other. They're not the same. They're in different places. They have different routes, but they're all consistent with each other to the effect that you will be able to ping from anywhere, arbitrarily ping from anywhere else in the network. Show IP route table, please. And I've learned some remote routes. Okay, let's see. I'm going to baby step here. I'm at R3. I'm going to go backwards. I'm going to try to ping one of R2's addresses. I'm going to try to ping the S000, which I hadn't been able to ping before because it's a hop away from me to on the other side of R2. Okay, let's see if this works. I'm going to ping the S000 interface of R2 is 10.1.1.2. It works. It pings. All right. I'm going to go even further. I'm going to go to the Ethernet port of R1. That's getting a ways away from me. So R1's gigabit port is 172.30.10.1. Quickly, it works. Hey, what about my host machine? Can I ping that address? Well, I can do this way. It was 10.3. It works. Okay, let's go to the host machine. Let's do the acid test here. Can PCA ping PCB? Can PCC ping PCA? Again, my IP address is 172.30.10.3, and in theory, I'd be able to ping PCC's address, which is 172.30.30.3. Bad magic. And we're not waiting for ARP. Wait for the time out here, and then let's troubleshoot this. Did I mess up an address somewhere or something? Wait a minute, I pinged that PC all the way from the other router. Let's go to, I thought I tested this already. We'll go to the command prompt. Did I mistype 172.30.30.1? Can I ping my own default gateway? I thought I did. 172.30.30.1. Yeah, that's okay. Can I ping 172.30.10.3? These aren't real machines. Is a firewall messing us up here? I'm going to try the 10.1 address, which is that PCA's default gateway address. Let's see if that works. Bad magic. I thought we already went this far back before and it worked okay. Did I inadvertently cut something off? Let's check our topology. Ooh. Okay, green, everything's green. Everything's done okay. Let's go back to router 2, the man in the middle. And from him, let's see what we get. Show IP route. There's not enough routes in this routing table. What's going on here? Did I show IP protocol? Did I finish doing this? 10 and 209.165. That's okay. I ping R3's 172.30.30.1. Oops, I'm sorry, I misspelled it. Now we're stuck in the DOS penalty box. Okay, that was supposed to be ping 130.30.1. Undeliverable. Oh. Do you know what I think I need to do? And I didn't do it? I think it's that automatic summarization. I think automatic summarization is killing us. So let me put that in there and see if that fixes it. Config T router rip no auto summary. I'll do all the others. So let's see if that fixes it. Because we've got a complex network here. Config T router rip no auto summary. And on the first router, T router rip no auto summary. And I'll try to be PCC again. 172.30.30.3. Let's look at the routing table for R2. Here's the man in the middle. Routes in there. It may take a moment for this to converge. No, let's check and see if PCB. We check and see if PCB, IP config, anything with default gateway 209.165.201.1. You can make this fine. Let's go back to router A and check his routing table again. And I'm just assuming here the problem is automatic summarization, and it's taking a moment to configure. Okay, so I think that's a good enough demonstration to get you guys started with this particular lab. The lab 3, that 3 lab on RIP routing. So please perform that. And I want to try to get, we're almost pretty much caught up here with our normal schedule. We've lost a week because of the extended spring break for 1 week. I'd like to get caught up by the end of this week or the end of the next week with our normal schedule so we can proceed through and be able to complete all the remaining chapters in the routing and switching essentials curriculum. I think I mentioned to you guys last time that we've changed the grading scheme. There will be no lab practical exam. Instead, I'll simply take all the labs that you actually are assigned to do, which is in the ICR Instructor Course Requirements and Syllabus, and you can see them in the My TCC Gradebook, and that'll be 50% of your grade. Complete those labs and email them to me with your last name in all caps and the file name, save as, so I can tell who they belong to. And then the other 50% of your grade will be the chapter exams. I've turned on all the chapter exams. You can take them. You don't have to wait till I cover that. You can take it whenever you want to. And your other 50% of your grade will be the average of all those. I think there's 10 chapters in this curriculum. And the final exam, so I'll add up all those 11 scores equally and divide by 11, and that'll be the 50% of your grade. Okay, guys, I'm going to cut you loose now, and have a great weekend trapped at home wherever you are. And we'll meet again on Monday, and we'll cover Chapter 4. I don't believe there's a lab for Chapter 4. So thank you for joining with me today, and I hope to see you guys again soon.